This is a continuation of the accumulation video that ended on part B of this free response. So let's go ahead to part C here. And in part C, they give us a function h, which is the integral of e minus L for 9 to 23 here. And they tell us the value of h of 17 is this rounded to the whole near number. So this problem's interesting here for part C because normally they say find the value. Here they give you the value and they're testing if you know what it means. And then they want you to find the derivative of this, find it at 17, and then interpret it as well. So this one is a lot of interpreting. So let's go ahead and take a look at h here. And this is where the units are key here. Remember, the units are the most important thing with accumulation. If I do E and L and I think about those are rates, remember, the rate in and the rate out. Those are both measured in people per hour. dx is the tiny width on the x-axis, which represents the time here, hours. People per hour, time hour, gives you just people. So this whole expression here, which is h, has a unit of just people. So that means that 3725 is the number of people in the park at 17, at t equals 17, which would be 5 p.m. All right, now I want the derivative. Well, in order to get h prime of 17, first I need h prime of t. So I need the derivative here, which means I need the derivative here. Well, derivative of integral cancels. FTC part 2 says you plug in your upper limits or limit of integration. Whoa, what am I doing? Times the derivative of that limit of integration, which is just 1. And so I just have the rate in minus the rate out. That's what h prime gives me. So if I'm going to interpret what this is, remember, if I combine my rates, they end up giving me that third mystery rate that they don't really specifically ask for, but you have to understand is going on in the background. Just like we had that third mystery rate going on here, someone was watching. Here, we have people entering a park. And then we have people leaving a park. If you don't know what those rates are and you're just someone who's standing there at the entrance of the park watching, the combined rate here would just be the total change or the total rate at which the number of people in the park is changing. I'm going to write that down. So again, you combine your rates and you end up with an overall rate. It gives you the rate at which the number of people in the park is changing, assuming that you don't really know what's going on details. It's just the overall rate. So now I want to actually find it. So I'm just going to do the rate in 17 minus the rate out at 17, and I get this. And I'm going to want to round that to the whole number. So I get negative 380. So h prime of 17 is negative 380 people per hour. So if I'm going to interpret that, this again is the rate that the people in the park is changing. And the fact that it's negative means that overall the park is losing people. So that means that it's the number of people, they're decreasing by 380 people per hour. So here's the interpretation here. Reading it sometimes is easier than just hearing it. And it's good to specify when your interpretation is going on, just to make it a little bit more specific. So there's part C for you. Let's go ahead and do part D. So part D says, at what time during this interval does the model predict that the number of people in the park is a maximum? So once again, I want a maximum here. And as soon as you hear maximum, you should be thinking derivative and derivative equaling 0. What I did for part D is I took the function that they gave me in the problem in part C. So if you look at part C right here, they already gave me this here, and I already interpreted h as the number of people in the park. So yeah, right here, we already did h of t as the number of people. So then because I want the number of people to be a maximum, I'm going to take the derivative of it, which I already did above in part C right here using the fundamental theorem of calculus, and I'm going to set my derivative equal to 0. So I have this statement right here. So now the question is, how am I going to know when e minus L equals 0? Because these are really ugly functions and I don't want to actually subtract them. Well, now you have to remember that this is a calc active problem and you already have them typed into your calculator, and this is equivalent to saying that the rate entering is equal to the rate leaving. So I'm going to go to my calculator where I have these typed into y equals, and when you do these, you have to be able to go to your window I ended up going from -1 to 23. I could have gone from 9 to 23, but I wanted to see the whole axis. And then I went to my table and I looked up to 23 and down to 1, and I saw that the highest it goes is a little under 1,100, and I went all the way down to -1 again to see my axis. So here's my graph. Blue is the rate entering and red is the rate leaving. So I want to know when these two are equal, and they're only equal to each other one time. So I'm going to go and I'm going to do an intersect. Whoops. So intersect. I need my blanket to be close, which it is luckily. So I'm going to do enter, enter, enter. And the critical value, which is when the derivative is 0, is 15.795 rounded. So t equals 15.795. That's the only possibility where there could be a maximum. And I know that this has to be a max because before this value, the rate entering is more than the rate leaving. And after this value, the rate entering is less than the rate leaving. So this is when there's the most amount of people in the park at almost 16 hours in. So that will be around 4 in the afternoon is when the number of people in the park is a maximum, which makes sense if you think about what Six Flags would actually be at around 4 p.m. That's when the most people are there. Okay, so that is part D right there, and part D was 2 points, 1 for stating this and 1 for your answer. They actually didn't require any justification, strangely enough, but let's go to a more recent one, which is from 2005. This is the most recent one we're doing. The previous one was 2002. The Sandy Point Beach problem is super well known. If you talk to pretty much any AP Calculus teacher, they're going to know the Sandy Point Beach problem. It's very well known in terms of accumulation. So here I have a beach, and the tide is removing sand, and at the same time there's the station that's pumping sand onto the beach, I guess to prevent the beach from losing too much sand here. So right away I'm going to say, all right, there's my Y1, there's my Y2, and I'm going to type them into my calculator before I even do anything else. Here's what my calculator looks like after I've typed everything in. Make sure that your mode is radian mode as always. So if I go back to the problem here, what I want you to do is mark this up. So mark down what you called Y1 and Y2. It's really important that you realize that R stands for removal. This is your rate out, and S stands for the station. That's your rate in. So they gave you the out before the in here. You do not want to mix those up or else the whole problem will be wrong. So units are important here. The rates are in cubic yards per hour, and we're only considering the first 6 hours here. And we actually have an initial condition here. In the amusement park problem, we did not have an initial condition. We do have one here. So I want you to pause the video, and I want you to do parts A and B, which are very, very doable, especially after seeing 2 of these. So pause the video and come back. For A, I'm going to do an integral of the rate out, and R of t is in cubic yards per hour, and dt is the tiny, tiny distance on the x-axis, which represents a little distance or a time. Those end up with cubic yards. So that's how you know that this integral is set up correctly. And on the calculator, I did this. I just called up Y1 because Y1 is removal, and I got the answer. And again, I'm not wasting time by rewriting my function. I'm just using R. For B, I take my initial condition or initial amount plus the rate in minus the accumulation of the rate out. Now, these are equivalent. This is just properties of definite integrals. You can write 2 separate integrals, which I will almost always do. Or you can combine them into one integral, which is totally fine as long as the rate out is negative. All right, let's go to part C. Part C says find a rate at which the total amount of sand on the beach is changing. So this is like that mystery third rate yet again. You have a rate in, you have a rate out, and then if you didn't know what those rates were and you were just someone standing on the beach noticing how the overall sand is changing, that's that mystery third rate once you have combined the 2 rates here. So in order to end up with a rate, I should be working with rates. So I don't need an actual integral. So what I'm going to do is take the rate out, take the rate in, minus the rate out and combine them. So I'm going to do it for S of 4 minus R4. Notation counts here. And just realize that if you end up with just this statement, that is equivalent to doing the derivative of this function right here, which is the total amount. Because if I do the derivative, this goes to 0. The derivative and integral cancel, you plug t in. The derivative and integral cancel, you plug t in. So you could also just call this y prime of t if you wanted, and y prime of 4. So let's do it on the calculator. This is where it's really important that you realize that y2 was the rate in and y1 was the rate out. So I get negative 1.909. And here's how we can say it. The total amount of sand on the beach is decreasing at a rate of 1.909 cubic yards per hour. Part D, once again, we're asking a maximum or minimum. Part D will pretty much always be a max or min problem. This time we want a minimum. We want to know during the 6 hours, when is the amount of sand on the beach a minimum? And this is crucial here. Not only are they asking when, which is what they did in this problem. Hold on. This problem here, they just wanted to know a time. This one is the slightly more involved one because they want to know not only when, but then what is the actual amount. Now, as soon as you see a closed interval and a minimum, the absolute minimum, you need to be thinking the extrema test. And the extrema test, if you don't set up the extrema test correctly, you will not get your points here. So extrema test look like this, remember? So I know my left point's 0, I know my right point's 6. I need to know my critical value, and the critical value is when the derivative is 0. And I want to take the derivative of y of t, which is the amount of sand. So I'm going to take the amount of sand here, y of t, and I'm going to do the derivative, which I basically already did here. Y prime of t, I said, was s of t minus r of t, and I'm going to set this equal to 0. That's equivalent to saying that s of t equals r of t. The rate in equals the rate out. Well, this seems really similar to the problem we just did, and it's because it is. The accumulation problems, once you do enough of them, they are pretty much the same idea every time. So we're going to use our graphing calculator to find out when those rates equal one another here. So there's the graphs. I'm going to go to second calc. Getting to intersect is something you need to be able to do very quickly. Okay, so here's your critical value, 5.118. Now there's two really important things to remember. First important thing is you cannot round this value. And to prevent yourself from having to write a 10-digit number over and over again, wasting time, what you're going to do is just call this a letter. A is just the first thing that always comes to mind for me. So you're going to say, hey, AP reader, let A be this, or whatever letter you're going to pick. And then for the rest of your calculations, you can just say A instead of writing this number. You cannot say 5.118 though, because then when you actually get the amount, that will be rounded and that might be off and you'll get that answer wrong. So the second important thing to realize is you need to go back to your main screen and you're going to store this as A. Your calculator is going to remember the last thing it found, which is the critical value. So those are two things you must do. I just wrote down those two things to remember. What that means now, to find the amount at A, I'm going to take my function for amount, and instead of T, I'm going to put A. So I take my initial amount plus the total amount pumped in up to A, which is 5 point something, minus the total amount lost up to A. So this is your in, this is your out. And then to get it at 6, I'm going to take the initial amount plus the amount in over 6 hours minus the amount out over 6 hours. Don't do anything for 0. They already gave you 0. That's the initial condition. Go to your graphing calculator. Here's what you type in. You literally put A here because you already stored it. That's saving you time. You don't have to type in the number again. This Y2 is in, Y1 is out. I get this amount. Now, to save yourself some time typing, just call up the previous thing, and wherever there was an A, just put 6. Here are my two amounts I get for the total amount of sand after 5.118 hours and after 6 hours. So I'm going to return to my table, fill in my actual values here, and make sure you answer the question. I want to know when is the sand a minimum and what is the amount of sand a minimum, or what is the minimum amount of sand. Wow. Okay, so the amount of sand is a minimum when T equals A, or you can just say the actual value. You can round here because it's your final answer, or you can just say A because you already said what A is, hours. And then the minimum value is this amount of cubic yards, because this, just look at your numbers, like this is the smallest number out of the 3. Okay, do the last 2 free responses. Quiz Monday. Bye.